So he got his PhD in physics in 2021 from Unicampi. And his advisor, he's a friend of ICTP-SAIFR, Tiago Alegre, that is visiting us pretty often. Then he did 3 years of postdoctoral activity in ETH in Zurich. And then at the end of 2024, he came back to Brazil and is currently a Jovem Pesquisador Fellow in USP, where he's now building his lab, right? You are in the process. Yes. He's an experimentalist, and he's working on general things in quantum technologies, and his expertise is, for instance, in optomechanics, superconducting qubits, and similar technologies. And today he's going to talk about superconducting qubits in hybrid quantum systems. Rodrigo, the floor is yours.
Okay, thank you, Dario, for the introduction, also for the invitation. I'm very happy to bring some of my very experimentalist knowledge to you guys, and I hope I can contribute a bit. And so, yes, as Dario mentioned, my expertise is basically dealing with microfabricated devices, particularly looking at these hybrid quantum systems. And today, I'm going to show you some interesting ideas and results concerning using these hybrid systems when we have somehow superconducting qubits into them. And so, yes, just to mention, yes, I'm working at the University of São Paulo now, starting my own lab that I'll briefly mention about now. But since I've heard that we have a quite broad audience, I think it's good to start from the very beginning, just to have everyone in the same page, the qubit itself. So, as we know, probably many of you know, it's basically, we start from it as an abstract mathematical construct, right? The idea of the qubit is something abstract where what we need to do, first of all, is to find some type of two-level system where we can control and operate the systems in a way that we can, construct using these two systems several different states, right? And then a general way of representing the states is using these angular variables here, where we see that all the states that we could construct with these two-level systems can basically form here the surface of a sphere when they are pure. And if they are mixed, we can also have them in the interior part of this sphere. We use this is a block sphere, right? We use this a lot in quantum information, especially to understanding what the gates and the operations are doing over our quantum state. But of course, I'll not just talk about this. I'm more concerned in the experimental part of it. So it's good to think what we can do with these qubits. And a lot of the results that you find in the literature are somehow connected to quantum computers, such as some resultings looking at quantum error correction using qubits in different implementations. Some other ones scaling up very much, up to more than 1,000 qubits and interconnecting and making operations between them. But also some different type of uses of this device, like improving the sensitivity of some quantum sensors, for example, in this case, for detecting a specific molecule in an environment, or even trying to use them as sensors for dark matter, for the detection of dark matter. So it's a quite flexible tool, and coming out from the abstract idea, I want to look a bit better of how we make them, how do we implement them physically. And since the needs that we have concerning these qubits are quite general, right? It's just like we need to have this system with a two-level system where we can somehow define a two-level system and make operations. We find many types of qubits, right? Many types of different implementations. I highlight a few of them here. Like we can have, for example, some defects in solid-state bases where we can work with these two-level systems, or we can have quantum dots. We can work in natural energy levels of neutral atoms or ions, and so on and so forth. And the way I connect all of those elements is that all of them are somehow using natural microscopic degrees of freedom of the system. And in this sense, I differentiate it from the superconducting qubits, because even though we have also a lot of different implementations of these superconducting qubits, which are normally seen like, you see different ways of implementing it, but a very important part that shows the flexibility that we have in this device is that here, instead of using the natural microscopic degrees of freedom, we are defining it by microfabrication, defining by the size of these circuits and this device that we're going to do here, what are, in fact, the degrees of freedom that we're going to be working. So we're going to have a lot of flexibility in the definition of what we call a qubit when we have these type of devices here. Yeah, so let's take a look a bit better on what they are. So they are actually, when we look at a superconducting circuit, superconducting qubit is not so different from an electronic chip that you would have in your phone. And in fact, since I work with experiments, I can make use of like some demonstrations, right? And so I brought a single qubit here that I will pass for you guys to take a look. It's a very simple one. Along the presentation, I will explain a bit better what it is, in fact, here inside. But you have a box, and inside it you see a chip, a small chip, also transparent, but you can see it, with some small electrical circuit here. So I will pass it for you guys to check, and please just give it back to me by the end of the talk, okay? Oh, well, the material itself is not so expensive, but all the tools that we needed to produce it are a lot of dollars. So, so you guys can take a look, and I will show a better picture on microscope later of it, right? So yes, so they are electrical circuits, microfabricated, which means that we go there, we design, and we define what's exactly we're going to be there. Where the most common materials, the only important need that we have is that these materials need to be superconductors at some point, right? So we normally use aluminum, by far is the most used one, but also niobium and tantalum, on a substrate that needs to have very low losses in the relevant frequency range, right? So normally silicon or sapphire, this one is made out of sapphire. So, and they have all the circuits that we work have two main elements. One are the resonators, which we'll see in some details soon. And the other one are the qubits themselves, the jewel there, right? And with these two basic elements, we can construct much more very complicated circuits that will do then more complex operations, right? So you see here, for example, we have here 2D implementations and also what we call a 3D resonator, which is the box, or a 3D-like qubit. This is just the definition on where is the electric field mostly in these cases. If it's 2D, are these two ones, and 3D is this one. And when you look at this circuit, you see that we have a lot of these wiggles here, which are the resonators for different goals here, depending on where it is. And also a lot of these star-shaped devices, which are the ways this group here define their qubits.
This is a single qubit, right?
Each of these stars here is a single qubit, but this whole system here, this one in particular, has 17 qubits.
Ah, I see.
Interconnected.
And so that means each resonator is a qubit or no?
No, the resonator is just a resonator. We will talk more about that. Each of these strings here, wiggled strings here, are different resonators, and each of these stars is a different qubit.
I see.
And then you can interconnect them, you can perform different things, right? But they are different independent elements, okay? So, okay, so to complete the understanding of that, let's look better at these elements. First of all, the resonator. What we do here, what we have here in this top picture here of the real resonator is more or less what we see here, where we have basically a central conductor, which is this central line here, which will be the brownish here. We have a ground plane around it, and also some excitation lines and eventually readout lines. So when we look at that, it's basically a bidimensional version of a coaxial cable, right? Where we have a central pin that would carry the information and some plane around in this coaxial cable. In our case, we do really as a plane over the chip, right? And as to model this device, what we do is normally look at we see that this central pin here will carry a density of capacitance and inductance along its length, so we can model it as a parallel LC circuit. It's a pretty simple electrical circuit, actually. And what we do, as you are probably very familiar with. We usually want to look at the Hamiltonians of the system to find the dynamics and all the properties that are relevant to us. So to get there, we start from the classical perspective, describing what you know how to describe, which is the energies of these elements here, right? For example, the capacitive energy and the inductive energy. But normally, in electromagnetism, we would define in these ways, but in our case, it's more convenient to use two other variables that it will become clear in a minute why, but we normally use charge and magnetic flux to define it. So if we have the individual components energy, we can have the total energy that will be, in this case, will be exactly the Hamiltonian in a classical way of this circuit. If you want to quantize this, what we do in this field is usually to do the canonical quantization, where we look to the Poisson bracket of these variables that we defined, and conveniently it is 1, which leads us to a canonical commutation relation between these variables. And with that, then we quantize this Hamiltonian that we had initially, promoting these operators to quantum operators. And then this is the basic Hamiltonian that will work for the resonator part of our system. So I'll just rewrite it, because when we look at that, maybe the most, some of you might have recognized that we have some standard elements here, which will allow us to describe this Hamiltonian as using ladder operators. So actually, this Hamiltonian can be simplified, rewritten in a very familiar way, right? So we see that what we are describing here is actually a quantized harmonic oscillator, right? So this, what I'm calling conveniently a resonator, is nothing more than an oscillator by itself, right? Where the energy levels will, as expected, be equally spaced, looking here, for example, to the lowest energy levels. So what I want to take out from this is just to remember that this LC circuit can be described as a quantum harmonic oscillator. And the same thing, I'm just describing this 2D one, but the same thing is valid also for 3D cavities. What I didn't talk about yet was why we use superconductors in that field, right? A first reason is because, indeed, to describe as a single LC, we need to ignore any resistance, and to having superconductors, there is a way to go into that direction, because they have nominally no resistance, right? So what we do when we scan, for example, a microwave tone around this, the characteristic frequency of this resonator, which we call a resonance frequency, we see a typical resonance feature here, where actually we can even find, looking at the line width of this resonance, find the lifetime of the photon that would be confined in the system. But we have a difficulty here when dealing with superconductors, which is the temperature when this becomes a superconductor, right? Because in fact, the qubit that you have in your hand is not a qubit now, because it's not a superconductor, right? It will just become a superconductor below 1.2 Kelvin. That's when that's where the transition temperature for the aluminum is. So if we want to use these devices as superconducting resonators, we need to be operating at very low temperatures. This is a first difficulty when dealing with this field. Okay, we found a way to describe them in the quantum mechanical sense, but we need to see how we operate, how we control any quantum state that we define there. And what we typically do is, when we have these energy levels, what we'll try to do is to change for example, assuming we start in the ground state, we can try to bring this system to the excited state by sending a pulse of microwave with the energy that can perform this transition. However, if after that I want to, for example, send my 1 back to 0, there is someone else I think still needs to see, right? Yeah. Okay. There's a problem here, because since all the levels are equally spaced, if my state is in the 1 state, in the 1 here in the energy, the first energy excited state. If I want to send it upwards or downwards, we have the same difference in energy here. So it's not clear what's going to happen. So it's not easy to control exactly what are the transitions that we are inducing. So the fact that this harmonic is nice, but we have a big problem that it's not so simple to control exactly what's the type of energy of state that we are describing in our resonator, that we are writing the resonator. So we have two big problems that makes us think is it worth it to work with superconducting circuits. And if it was just because of the resonators, probably no, because we have a lot of other harmonic systems that are much easier to be operated, and many of them are even possible to be operated at room temperature. But what's important in this field...
Rodrigo,
yeah.
What determines the convenience of going, let's say, because you say this one, for example, is aluminum.
Yeah.
That is the one that is the lowest temperature. So is it more convenient to work with aluminum and have to go to lower temperature, or with another material and you can stay a bit up in temperature? So
yeah, it's a good point, right? A first question that some people do is like, oh, why don't you use like these high temperature superconductors, something like high, like 70 Kelvin or so, right? The problem is that we need to microfabricate these, right? It's not just that you need a block of the material. You need to be able to make, first of all, very good films on a chip that we can then make lithography, and there's all the fabrication process that make it harder to get there. So there's a finite collection of materials that we can start to work with, and usually they are the simple, so far, you know, like are the simple superconductors, the type 1 superconductors, and usually like pure materials or some simple compounds here. But and then aluminum is a very even comparing that, you can ask like why aluminum, why niobium? Aluminum is the easiest one. That's the point.
So there is a consensus about among the various companies on which one. So like everybody works with aluminum, or
it's a big part of the community works with aluminum, because when we have these temperatures, you normally need a dilution fridge, and then if it's 1 Kelvin or 4 Kelvin, doesn't make too much of a difference, honestly. But there are good reasons. There's a good trend in the community to change to tantalum. From last 2 or 3 years, people have started to move to tantalum because of other reasons. And in summaries, like the quality of qubits that we get on tantalum are showing to be better than the ones that we have on aluminum. But it's still like an open field, you know, like could be that someone discovers a new material that's more convenient and then everyone shifts again, you know. But at the moment, yeah, 95% of the works you'll find are made out of aluminum. Okay. But as I mentioned, yes, just to continue, if it was just because of the resonators, probably would not work with superconducting circuits, but we have the qubits, and to understand the qubits, it's good to briefly talk about the superconductivity itself. So a superconductor, a block of superconductor, is composed of a condensate of Cooper pairs, right, which are these coupled electrons. So if you look at it, you have a lot of electrons coupled in pairs via phonons of the lattice. And an important point for the discussion here is to know that all these electrons will be, these Cooper pairs, will be defined by a single macroscopic wave function that carries a specific phase here. And this is important because when we do a different thing, instead of having a single block of superconductor, we put an insulator in between them. It seems initially that things didn't change much because we still have Cooper pairs in both of the sides, and these Cooper pairs could tunnel from one side to the other, right? However, in one side, we could have a specific phase phi1, and here we can have a different phase. What this leads to us is that the current, the tunneling current that we observe of Cooper pairs here will carry this phase difference between the two superconductor islands. And for us, this is very important. Why? Because current is directly connected to inductance. So using a Josephson junction, it's a way of constructing a nonlinear inductor. So if we go back to our LC circuit, and instead of a linear inductor here, we exchange this for one of these guys, a nonlinear inductor, we can go out of this completely harmonic system that we had before and define in a controlled way what's the anharmonicity that we introduce in this harmonic system. We control because we can define what is the thickness, what is the size of this insulator layer here, and this will define basically the degree of nonlinearity that we'll have there. And we can control it so well, such that, for example, we can choose a pair of these states, which has a very specific frequency transition and very different from, and very different from all the other ones, in such a way that we define here a qubit. This is the binary base that we work, and normally we just select the ground at the first excited state. Yes, go ahead.
Thank you. How do you guarantee that you are using, let's say, the two lowest levels and not any other? I mean, or that, for instance, you will put your information in the one on the top, and then it will ionize, and then you lose everything. How do you guarantee that?
Yeah, so if you check really the energy levels that you have here, because of the nonlinearity that you will just basically change from the harmonic one for something that continuously decrease or increase depending on the sign of the nonlinearity, but normally we make it always decreasing as you increase the number of the levels, right? So all the frequencies will get always lower as for the upper levels, right? And what we typically do is try to separate these frequencies by design. This is something that we design, right? Separate these frequencies well enough such that when we send a microwave tone around here, we know that we are not communicating with these lower frequencies, right? But it's still possible to access these other transitions. And there are situations that we even go out from the binary base, and you can use the third level, the fourth level, if it's convenient, right? But the standard is try to avoid to separate these spectrally and just work in the range that is inducing this single transition here. Okay? Thank you. Any other question? Feel free, okay? Yes, so if this is done well enough and we isolated it well enough from the other states, we can even define this Hamiltonian as a two-level system Hamiltonian. And normally, for this type of device that you check in your hands, the frequency range that will work for these qubit transitions is on the order of a few gigahertz. So this is the picture of not exactly this device, but a very similar device that we fabricated there. So what you had there in the chip, it's a microscope image here. You had really like the two plates that you could see, which form the parallel plate capacitor here. And here at the very center, you have a very small thing here, which is the Josephson junction, right? Which basically is this layer that I was describing here, right? You see that we have in the scale here 400 nanometers, so it's a few hundreds of nanometers wide, this junction. And now the control is more precise, right, compared to the resonator that we had before. Because what we do is what we just discussed now, right? If we send a wave of pulse now that has exactly this frequency given by this transition here, the qubit undergoes the transition that we want to have, right? And we can control how much we go from one state to the other, right? But if you use any other frequency, we don't change this binary base that we were working on. Something else can happen, but not there. So in that sense, using electromagnetic pulse, we can build, in principle, any arbitrary quantum state that we wanted into this qubit. Okay? Cool. Now that we know roughly what they are, how to control them, we can think about the readout of this information, right? How we read these two elements. For the resonators, it's quite straightforward because what we typically do, we have, as I showed in our toy model, this is a resonator, right? And you have then a capacitive coupling in both sides. And we can, for example, send a microwave tone and measure the transmission of this microwave along the system. And what we have sweeping this microwave tone is a typical, it's just what we described in the theory before, right? We have a single transmission here where we can define the resonance, the frequencies, and the lifetime of this. So this is actually a semi-classical measurement because you are sending a bunch of photons and just checking how many get transmitted, right? So it's quite simple to define, to make these measurements. But when we go to the qubits, because if it's a two-level system, just one photon can be absorbed at a time, right? So we would need, if we want to do something similar to that, we need to have something sensitive to single photons at the end. So this is not possible, so far at least, right? So we need to think about other clever ways, more clever ways to do that. And what we do then to characterize the qubits is to think then, if you remember, I told you that these qubits will have these Cooper pairs that will be basically tunneling from one side to the other, oscillating here between the two poles here, right? So what we have here in the end is basically this oscillating charge defines an electrical dipole for this element. Then if you bring this close to these resonators like this one here, this resonator has a specific profile of electric field here, which we can bring like conveniently close to this dipole system now, and have really a dipole electric field interaction here. So we can look at this. We can, again, make the same type of quantization that we did before, and we can look at then at these elements, at this interaction as the Hamiltonian interaction between now the system resonator plus qubit. Just to show a bit better how these elements look like, the dipole matrix here will be an anti-diagonal matrix that we can just use the Pauli matrices to write it. And for the electric field, we typically can quantize in the standard quantization method. And what we have then, the Hamiltonian interaction Hamiltonian here, well, we have this format where here I will make just a few approximations to get to a convenient expression. One is energy conservation, and the other one is assuming that the resonator frequency and the qubit frequency are quite far apart. We'll see why this is important in a second. So we get to a Hamiltonian here. Well, this is actually this term becomes this third term, the interaction part, and I'm just writing then the full system Hamiltonian, which carries the resonator part and the qubit part plus the interaction. I'm just going to rewrite here because we're going to take a look at that. This is a very important Hamiltonian in this, this field because it gives us exactly a way to read out this qubit. If I rewrite this just like showing up, highlighting here this expression, what I want here, what I want to show here is that what we had before was, in the separate system, if you don't have any coupling, we have just a resonator with its given frequency, what's its bare frequency, but now we have an effective resonator frequency that's dependent on the state of the qubit. You see that we have the sigma z here that carries the information from the qubit, right? And this has two possible eigenvalues, +1s and -1. So this shows us that now, depending on the state of the qubit, the resonator resonance frequency will be modified. And in fact, is what we see when we do then the same microwave sweep along the qubit, along the resonator frequencies. Now we'll have two different results, two different outcomes. If our qubit is in the ground state, we'll have a positive shift here, and the frequency of the resonator will shift to higher values, right? And the opposite if it's in the excited state. So what we would do now to characterize the qubit is look at the resonator. And that's how we do typically in a daily basis there in the lab, right? For example, you can just have, instead of sweeping the whole system, you can just keep a microwave tone at one of the resonance, for example, here, right? And keep measuring it And if you measure in this example something like 1/2, you would know that your qubit is at 0. If you measure it there in the top would be the red, something close to 1, you know that your qubit would be at 1. So this is basically, if you have very few photons for this measurement, it's a quantum non-demolition measurement of the qubit in your system. Okay? Okay, now that we have most of the, basically all the basic fundamental elements to this field, I'm going to show a few experiments that show how flexible and how good these systems are to perform different, to construct different quantum states. A very important seminal work in this field was this one from like about 15 years ago. And what they have done, the circuit that they have there is very simple. It's actually just a qubit, like we have discussed, with a few specific elements that we'll discuss in a moment, but it's a qubit very similar to what you just said, coupled to the resonator in this dispersive way that we just mentioned. We have some drives here, both for the qubit and for the resonator, to induce some excitations to them. And there's a system here that allows us, what it does is it changes locally the current in a controlled way, such that we can induce an additional inductance to the system. And this leads to a change in the frequency of the qubit. So this is a very nice way to control the transition frequency of the qubit that we have here. And with that, we have all the knobs that we need to control the system, because we can excite the qubit in a very defined and controlled way, and change the frequency of the qubit, and for a given amount of time, interact with the resonator, and then take it out of resonance again. What happens in that case? You have now a two-level system interacting with another system, in principle, in the ground state. What we have is that we start to see Rabi oscillations between the two systems. So if you cut here one horizontal line here, for example, at 0, this is the detuning between the resonator and the qubit. If you cut a line, you will see like an oscillations here. It's just like this quantum of energy going from the qubit to the resonator to the qubit and so forth. So if conveniently we stop after one full swap has happened, we know that the excited state that I have sent to the qubit now passed to the resonator, and the qubit's back to the ground state, right? And we can do this. Remember that the resonator is a bosonic system, right? So we can put 1, 2, 3, any photons there if you want, right? The qubit just can have 1, but this is good because we can always know how much we are giving to the system, right? And this is what they do here. They try to climb this ladder with the resonator and write very different, several different Fock states now in the resonator, right? So this is just Wigner plots of the states written in the resonator by means of this type of interaction here, right? So you see that they showed here for, I think, the first time a very big flexibility of the type of states that they can write in the resonator. And you have these very beautiful plots, right? These are the simulations, and these are real measurements of tomography measurements of the resonator. And people went further with that, right? Like having this type of interaction here and changing a few more knobs, they could do more complicated, more non-classical states like cat states, also with a sequence of operations using 2 cavities now and 1 single qubit. They could also define this, which is the famous cat state, right? Where you have like 2 blobs here, which would be the classically distinctable elements, and we typically see some fringes of interference here in the center. These states are actually super good and have been, in the last few years, being explored as a way to encode information to make qubits and go to quantum computing using actually just the cat states instead of the qubit states, using these bosonic-based states now.
So here, let's say the quantum device that carry all the information and so on is the resonator. The qubit is just what provides, what build the state, right? But then the state lives in the resonator.
Exactly. Okay. This is a Wigner plot. Both the previous slide and these ones are Wigner plots of what is in the resonator, right? And you use the qubit is your tool. It's really like the tool that you go there and build your quant state. But the resonator, because since the resonator is this harmonic system, you have more freedom on what you could, in principle, write there, right? The qubit is a more restrict space.
One qubit, because everything is
not all that, I wouldn't say all the time, but so far, yes.
Okay.
Yeah, but there are situations that you need more qubits, one you need like as ancilla, and it can scale up, right? But so far, yes. And just another example, beautiful example, much more recent, that they also have been exploring these states called GKP states. Again, a Wigner plot of what's written in the resonator. But these states are also very interesting resource for quantum computing because they are less sensitive to photon losses, basically. Because if you have one photon lost in the system, you basically shift all this grid by 1 square, and you are in the same place again. Sorry. So this is the main interest in this type of states, these so-called GKP states. But what I want to highlight is that the superconducting qubits allow for a great flexibility in the generation of these non-classical states. And honestly, I believe is this type of system that gives the most flexibility that we have so far, right? Compared like to optics or even like to atomic systems, right? The flexibility that we have here is really unique. Cool. So just summarizing this part, like these elements, this resonator plus qubit form what we typically call like the quantum electrodynamics of circuits, right? And all that you can do from these elements, right? But these are the basic tools from quantum electrodynamics of circuits. Okay, so far we had like these two-level systems, in our case the qubit, interacting with a microwave cavity, which is a harmonic oscillator. And then the question that come up is like, is it possible to do the same with other types of harmonic oscillators, right? Can we go to another bosonic systems there? And probably yes, right? Otherwise, I would not be asking this, but that's what I want to show you. And these are, in a sense, it's where we enter in these hybrid systems, right? We will try to exchange these elements here to other elements. And a field that's very successful in this realm is the field of quantum acoustics, where we will now exchange these harmonic oscillator by really mechanical oscillators there. A very good example, that was one of the first ones that could explore a lot these quantum acoustics, is this one done 8 years ago, right? Where they have, what they do here is now 2 chips, similar to what you were seeing, but we have one that's just a qubit like we had, but we have a second element here that will host, it has this dome here, that will work as an acoustic Fabry-Perot cavity. So it's like an acoustic mirror, 2 acoustic mirrors, right? And you have like mechanical waves going back and forth. And here we have a piezoelectric film. These piezoelectric materials are the materials that can transform electrical field into acoustic deformation, right? So the idea is to have then the electric field of the qubit interacting with this piezoelectric layer and creating this acoustic excitation. And the opposite also happens, right? If you have an acoustic excitation here, you will excite this piezoelectric layer and create an electric field that can interact with the qubits, right? So it's a two-way interaction. And here the idea is to do this first important paper of the field. The idea is to do the same thing that we saw in the first one that had just a qubit and the microwave resonator, right? Again, you use the qubit to create the states, right? The single quantum there. And then you can put the qubit on resonance with the phonon and take it out of resonance again. In the same way, climb this ladder now, but with phonons, not with photons anymore. And what they do is that they show what we would expect, right? You can write like the different Fock states here. This is a 1, this is a 0 plus 1, this is a 2. And it's the first demonstration, I believe, that has shown like how we can write Fock states, and they went up to 7, if I'm not mistaken. You can climb this ladder with phonons now. It's really the control of acoustic excitation at the single phonon level now. You can also think in other ways of implementing this quantum acoustic interaction. For example, you can use, instead of a single layer of piezoelectric material, use the whole substrate as a piezoelectric and use some electrodes that do the same kind of thing that we just discussed. The difference that one of these electrodes will be somehow connected, interacting with the qubit, and then we will induce the deformation here. And this deformation can be done in a way that will generate these ripples here in the surface of the substrate that are called surface acoustic waves. So you can make your phonon propagate along the material here. And some people proposed that, so the idea would be to have a qubit here that interacts with the second chip that is just like this guy here, and creates this excitation, and then you just have the reverse of this idea, right? So you catch the phonon with the electrodes, interacts with the qubit again, and would be able to measure it. And the same group, after a few years later, was able to demonstrate that in a very beautiful experiment here, where they have then again the qubit, these electrodes, in the same in the other side. We can ignore this for a second. The first thing that they do is literally a launch and catch experiment with these phonons. So you have here a single photon generated in the first cavity, in the first qubit. It interacts with the phonon, and then you lose it. You cannot measure it here anymore at this side because it propagates, and then you don't measure anywhere. And then we start to measure signal in the second qubit, which indicates that the phonon has arrived here. And they also did a second experiment that's even more beautiful, which is using this first element didn't have this central. This first experiment didn't have this central element, but then they introduced here a beam splitter, just like we do for those familiar. Sorry, you can go ahead. Yes, don't worry. Yeah. So the phonon is propagating in the substrate, right? It's really an excitation of the whole material, right?
So it's not a fundamental object, right? It's some effective object, right?
So you can think of it as a mode. We can talk in that sense as well. It's a single excitation of a mode that lives in the whole chip here, right? It's a mechanical mode. If you write the equations of motion, Newton mechanics by itself here, and you find, but in the continuum, you find that a mode can live here between these two electrodes, and this is a single excitation that we call phonon of this mode.
Okay. And is the reason to do this, is there any reason why this is better than the other method with photons, or is it just a different method?
With photons, you mean?
Yeah. Why would you prefer to do acoustics than to do?
So, first of all, because it's cool, it's a fundamental, but we'll see in a second, this is connected with some experiments that we cannot directly connect to just with photons, right? The idea is to explore these hybrid systems, right? Like, first of all, there's a fundamental interest of like, can we do the same that we do with photons, with phonons, with these other excitations of fields, if we want, right? Like, and what we show here, what they showed here, is that yes, in principle, the same logics that we use for making quantum optics by itself works identically with phonons instead of photons, right?
So quantum mechanics is the same. There's a single phonon which has a fundamental frequency and all these things just like a photon?
Exactly, that's the idea. Okay. And for example, maybe for those who are familiar with quantum optics and are familiar with the Hongo-Mandel experiment, which is when you send, the Hongo-Mandel experiment it happens when you send two single photons into a beam splitter, and because of interference of the wave function of these photons, they bunch. They either, so here's the beam splitter, they send the single photons now, and because of interference, they either will go both to the side or both to the side. And then what happens, this is a very traditional experiment in quantum optics. If you try to measure the coincidence measurement chance, the chance of coincidence measurement in the two qubits, when they are, the phonons are incident at the same time, you see this bunching happening. So you don't have coincidence measurements, which indicates that they either came here or came here, right? So you see that's a very fundamental experiment of quantum optics with phonons now. And I think, well, I think this is pretty interesting to see happening, right? Yeah.
Although, I mean, it may be very difficult to do, but I mean, how far can you send this information with phonons, and how far could you send it with Nathan's idea of putting photons? I mean, can you use it to send, let's say, send messages?
So, depends on what you want. So, phonons, you can, best case scenario, I think, propagate centimeters. With photons, there are experiments that people are sending to satellites and sending it back, and you are keeping the information, right? So if you want to propagate it far, photons are much better. But there are reasons why, we'll get there in a few slides, but there are reasons why sometimes you want to use phonons. But a good way to think of it is that a phonon mechanical movement interacts with almost everything. You can couple it with qubits, we can couple it with light, we can couple it with quantum dots. So it's a system that, for the good and for the bad, interacts with basically any other system. So it's a very good intermediate of quantum excitations, right? So that's an important interest in talking about phonons here, about quantum acoustics, right? Okay? Thank you for the questions. Yeah, I think I conclude here, right? Yeah, so yeah, that's the idea of the experiment. Okay, now let me just keep track of time, some 5 minutes here. I'll just mention what we are doing now in the lab, starting to doing our lab. So we just, as Dario mentioned, we just started early this year the Engineered Quantum Control Systems Lab there at University of São Paulo, where we want to focus on this microfabricated device with interest in these hybrid systems. And we were lucky to get a generous grant approved by FAPESP together inside this QT call for quantum technologies to do a microwave to optical quantum transducer. And I'm gonna mention a bit about this project now. So the idea of the transduction comes from, well, we just discussed these quantum chips, right? The quantum superconducting circuits chips, which are operated in the few gigahertz range. But then if we look at the thermal occupation of these frequencies, we see that we'll just be below the grounds, the one of occupation, what we could call a ground state at very low temperatures, right? Below 300 millikelvin or so. So we need to operate at not just because of the superconductor, but also because of the frequencies that we are operating in. We need to operate at very low temperatures. That's why we use these tools that you might have seen already, which are the dilution fridges that are in the few millikelvin regime. So if you want to make a network of these quantum processing units, somehow interconnect two or more of these elements, you need to find a way to make it happen, and this is a big challenge. There are some people trying to do that. There was a first effort on doing what I call a brute force option, which is really do a very long dilution fridge. In the case of this experiment that they have done in Switzerland, with a 30 meters long dilution fridge, which is great, but of course is a very expensive way of doing that and unfeasible for a long distance. So it's not really a way to do that. We can go naively and try to directly connect these using microwave cables to connect more elements like this. But when we go out of these fridges, if you continue plotting this for until room temperatures, we see that at room temperature we are far away from the ground state, right? So also not a way to keep the coherence of these quantum states that you defined. That's why us in our group, but also some other groups abroad are trying now to go what I call a reasonable option. That's to interconnect these elements using optical fibers, so optical frequencies, because when we are at these frequencies close to 200 terahertz, we see that even at room temperature, we are still far deep in the ground state, right? So the optical fibers are very good quantum channels even at room temperature. And they are also very low losses, are compatible with infrastructure, right? Cheap, and yeah. So there are a lot of good reasons to do the communication, the long distance communication using photons instead of using optical photons instead of the microwave photons that we had before. And then we could directly try to connect these superconducting qubits with optical modes. It's a way. It's the first approach I think that people would try. And some people have tried some type of directly electro-optical coupling, but there are a few problems. One very important one is that what we call a quasi-particle generation, because the superconductors, they are this condensate of Cooper pairs, which have an energy gap here. This energy gap is defined by the material, but always in the order of tens of gigahertz. For aluminum, it's 43 gigahertz. And then if you send energy enough to break these Cooper pairs, you create what's called in this community the quasi-particles, which are these electrons now free to move around the elements, and they induce the coherence to your elements. And we even explored this in a recent paper where we really shine light directly onto the qubits. And we see that even for very low powers, in the nanowatts range here, we already, this is just like different positions of the laser in the qubit, but we see how we introduce the coherence, we reduce the lifetime of our qubit by increasing the optical power here. So, in summary, in a nutshell here, what I say is that these broke Cooper pairs lead to decay of the coherence, so electro-optical coupling is not a good way to do that, actually. That's why some people are thinking about using an intermediate here. That is where coming the mechanical oscillator, right? And we saw already that electromechanics is something that works very well, right, when we connect these two guys. We didn't discuss this other part here, so I want to mention in 1 minute what's happening here, basically. And with that, there are a lot of experiments of optomechanics, a very rich field, but I will, for obvious reasons, highlight one of our works that we have done, which I think is a nice work that demonstrates that, which was the first quantum teleportation using optomechanics. So in this slide, is the only one that you don't have any superconducting qubits, okay? Just to show. What we had here was these optomechanical elements, which are just like what we call a nanobeam made out of silicon, where we drill holes in a specific way to confine optics and mechanics, acoustics in the same region here. And in this sense, we create a very strong optomechanical interaction. And then what we do with this pair of elements is, you see here that we have a waveguide and two elements here at the sides that are where we confine the optical and mechanical modes. And then what we do now, I will not go into all the details of this setup, but I'll just highlight the important ones. We encode a mechanical qubit, what we call a mechanical qubit, in a pair of bosonic elements. They are still harmonic. They are not really a qubit itself, but we just, with very low probability of excitations of both elements, we can call this approximately, this pair of elements approximately a qubit. So we use that. We use another arm here of this setup to construct optical states that will be teleported to these mechanical qubits. And here in the end, we have a pair of single photon detectors that can perform Bell state measurements of what's happening here. So what we do is to, for those who are more or less familiar with quantum information, is the standard teleportation port protocol that we find in literature. So we first encode, as I mentioned, encode a qubit onto this pair of mechanical oscillators, entangle them with a single photon that we send through this interferometer here. This photon here will get to this beam splitter and interact with a photon carrying the information that of the state we want to teleport, and then we perform a Bell measurement. When we do this Bell measurement, the state that was in this arm is teleported to the pair of mechanical oscillators here. And then in the end, we just send another optical pulse to check the mechanical state, to check if in fact we had this. And well, we have done this experiment there. It was tough, but we were able to make it, where what we are doing here is just working with the polarization of the photon here, horizontal, vertical, diagonal, anti-diagonal, and teleporting it to the mechanical states and checking if indeed we had it. This is the fidelity that we are measuring. And we see that we could show that all of them were above the 2/3 line here, which is the classical boundary where we could get potentially with only classical resource. So above this, we show that needs to be quantum, right? So this is a nice experiment that I think demonstrates that these optomechanical elements can also be operated in carrying quantum information and can be a good intermediate for these mechanisms that you want. Okay, almost there. So now we have this whole system, and as I mentioned, mechanical modes interact basically with everything. So the idea that we want to do for our transduction is then excite our qubit there, perform some type of swap, like we have done already with the electromechanical systems, and some other swap for the optomechanical systems now, interaction, and then we have an optical photon in the end. And this is what we are starting to work on there on the, I'm almost done, just to, I think I passed some time. But this is what we're trying to do there at USP, where we have a full system here that will try to do that, composed of many elements. I'll just highlight a bit of them. We have the superconducting qubits, where I have two students working on. So the idea is to make this an harmonic potential that we just discussed. Not to enter into details on that, but just the geometry implementation. And the difference here is that I'll connect these qubits with an inductive coupler that will create magnetic fields. And these magnetic fields will interact with the electrodes in the layer, piezoelectric layer, that will form our mechanical oscillator. Natalia is working on that, our student as well. So it's just the thing that we briefly discussed, right? One of them, the electrode arms here is connected to the qubit, one is in the ground, such that we create these ripples here, right? And just like replicating basically what has been done in this work that we discussed. And finally, we are working on implementing an optomechanical device also for these, where we are constructing a micro Fabry-Perot cavity, where we are building some micro mirrors inspired by this work here. And the idea then is that these ripples here will interact with the optical cavity here and modulate the optical cavity frequency such that we can remove information from the system. This is the interaction Hamiltonian, but I just want to highlight that's parametric Hamiltonian that is enhanced, the coupling of this interaction is enhanced by the cavity number of photons in the cavity, and this type of cavity can sustain a very high number of photons, so we believe that we can increase this interaction very much. And that's it. Like, our group now actually is just an empty lab that we are still renovating, so that's where we begin, right? We need to start from somewhere, but we are now in the process of acquiring a dilution refrigerator that I hope by early next year will be installed here in our lab. We are also installing, already acquired some of the tools to control the qubits, and also all the tools for the optical setups, which include lasers, optical tables, and so forth. Okay, just recalling, we talked about resonators, qubits, what we can do with these qubits, and also a bit about this transduction protocol and how we particularly at USP are working towards that, okay? So I invite you to check our website, and thank you for the attention, also the funding agencies, and thank you for the attention.
Thank you very much for this pedagogical talk. Questions? Let's go first with the...
Hello, thank you for the talk. How can you guarantee that the phonons in your piezo are quantized? Just lowering the temperature is enough? Because you just have a signal, the piezo stretches or wiggles, and you have mechanical waves, right?
Yeah, so the idea is that we can, it is a bosonic system, so we can just calculate the Bose-Einstein occupation of it at the temperatures that we will use, right? So if you go to the millikelvin range that will be inside this dilution fridge, we need to be there, right? Like if you put at classical temperature, at room temperatures, you're not gonna get in the ground state, right? But if you cool it passively, you know that almost approximately, almost all of your phonons are out again, are already of the system, so you are in the ground state. And then you know that any excitation that it was created there in principle was due to your electromechanical interaction or optomechanical, right? So it's basically you cool down it to remove any thermal excitation, right?
Okay, okay, thanks.
Thank you.
Thank you very much. Very nice talk. I want to, in one of the first slides, you showed possibilities of systems that could be qubits.
Yes.
Okay. One of them was Rydberg atoms.
Uh-huh.
So, I mean, I never worked with Rydberg atoms, but I had a slight idea. So isn't the Rydberg atom too near, I mean, the levels, are they too near ionization that you could use it as these two stable levels that you need?
Say it again, the end,
I mean,
sorry.
you need, to have a qubit, you need two levels that are very well separated and very far from the rest. So then in Rydberg atoms, aren't Rydberg atoms meaning that the levels are very near, all cramped, very near ionization?
Yeah, it's a good question. Honestly, I know very little of this, of Rydberg atoms in particular, but what I know is that they are operating at, as you mentioned, the very high level, like 69, 70 of excitation, right? And then the transitions, but I think I'm not sure about that. To be very honest, I can't give you a very precise answer about that. I know that they are operating about some of these transitions. Yeah, and I know that's a very good system. I showed the first paper there, where they have the biggest number of qubits interconnected so far, which is 1,000 and more. I think they already reached like 4,000, if I'm not mistaken, is with Rydberg atoms. But exactly what are the transitions, I'm not sure. But what's good about them is that you can, just using lights and diffractive grating, this group at Harvard has shown this, that you can operate many of these in coordination, right? So today, like I would say that today, the two main platforms for scaling up quantum computing are superconducting qubits and Rydberg atoms. But the detail of the transition, I might need to check better to give a good answer to you. But it's a good point, yeah. But in the end, I'm sure that they are operating between the very high level of excitation there. But exactly what are these frequencies, I'm not really sure, honestly.
More questions? Perhaps a very naive question.
Yeah.
I mean, you showed that to go from a resonator, I mean, from an harmonic oscillator to a qubit, you need to put an harmonicity, right? But so the more anharmonicity, the better, or?
No, not necessarily. Not necessarily. For example, if you get the first thing people in this field, people tried was like to put a lot of anharmonicity, but it was so anharmonic. it was the type of qubit called charge qubit. It was a superconducting qubit in the early 2000s, but it was so anharmonic that was sensitive to charge fluctuations of whatever is around your qubit. So like someone entered the room with a cell phone, and then the frequency transition of your qubit inside the fridge would change. So what you do is that you make it anharmonic enough such that your energy levels are separated, but flat, like not anharmonic enough such that you can hold some change in the environment. It's not so sensitive. But it's a good point, right? And it's also in the end a bit of design, right? How much you want to go into one or the other direction.
And you showed at the end, let's say, an experiment that you did, but I guess that was still in ETH, right? You were using the facilities of, okay.
Yeah, the experiments, the teleportation was in Delft during the PhD, and the other one with qubits was at ETH. So here I still don't have experiments running, unfortunately. Yeah. But soon we're going to solve that.
Okay, yes, yes. Are there any other questions? Okay, if not, we can thank Rodrigo again.
Thank you all.